Hello, and welcome to Space for Sleep. Mercury looks like the easiest planet to dismiss. It is small, airless, scorched by the sun, and covered with craters. From a distance, it can seem like a leftover moon placed too close to a star. That first impression is wrong. Mercury is the planet that forced astronomers to take Einstein seriously. Its orbit carries a measurable signature of curved spacetime. Its day lasts longer than its year in the way sunlight moves across the surface. Its core is so large that the planet is almost an iron world with a thin rocky shell. It has a magnetic field that a planet this small should not easily maintain. It has water ice hidden in permanent darkness, only a short distance from terrain hot enough to melt lead. It has cliffs hundreds of kilometers long, formed as the entire planet cooled and contracted. It has bright, strange hollows that seem to be eating into the surface today. Mercury is not simple. It is small, but it is not minor. It is quiet, but it is not empty. It is one of the most compressed scientific puzzles in the solar system. A world where relativity, tidal forces, planetary formation, magnetic dynamos, volatile chemistry, solar wind, and ancient impacts all meet in one dark, battered body close to the sun. The story begins with a planet that human beings could see, but could barely study. Mercury was known to ancient observers, but it was not easy to find, and it was rarely comfortable to study. The problem is geometry. Mercury orbits closer to the sun than Earth does, which means from Earth's perspective, Mercury is never very far from the sun in the sky. At its maximum elongation, its greatest angular distance from the sun, Mercury is only about 28 degrees away. That's not much. In practical terms, it means Mercury is only visible in a narrow window just after sunset in the western sky or just before sunrise in the eastern sky, when it appears low on the horizon for a brief period before the sun's brightness overwhelms it or before it rises above the horizon properly. This geometry made Mercury difficult to observe, well, even with a telescope. Galileo never observed it clearly. Even professional astronomers of the 17th and 18th centuries found Mercury frustrating. It appeared in the twilight sky, at low elevation, where atmospheric distortion is worst, for relatively brief periods, and its small angular size meant there was very little to see even in a good telescope. The surface of Mercury remained completely unknown through the entire era of classical astronomy. The famous astronomer Nicholas Copernicus, who upended the understanding of the solar system by placing the sun at the center, reportedly lamented on his deathbed that he had never in his life managed a satisfactory observation of Mercury. The planet is visible without a telescope under good conditions. It can reach a magnitude of -2.4 at its brightest, making it outshine most stars, but it appears in the sky for such a brief period before being lost in the solar glare that casual observation is difficult and productive scientific observation is harder still. The best observations of Mercury from Earth were always frustratingly limited, and scientists who studied the other planets with growing success found Mercury perpetually elusive and resistant. The ancient Babylonians tracked Mercury's movements as early as the second millennium before the Common Era, and their records show they understood it as a single object following a regular pattern despite appearing alternately as a morning and evening star. The ancient Greeks initially called the morning and evening apparitions by separate names. In the morning, Stilben, and in the evening, Hermes, before eventually recognizing them as one body and settling on the name of their messenger god, a fitting association for the fastest moving point in the sky. The Romans gave it the name of their equivalent messenger deity, Mercury, and that is the name it has carried through to the present. For most of human history, Mercury was a moving point of light that could be tracked and timed, but never properly seen. It was not until the 20th century, and ultimately not until the space age, that the surface beneath that point of light began to be revealed. There is also a deeper reason Mercury resisted easy understanding. The planet spends most of its apparent life close to the Sun from our point of view. It appears briefly, then vanishes into glare. It never rises high into the midnight sky the way Mars or Jupiter can. It does not offer long, comfortable observing seasons. It does not sit in darkness waiting patiently for telescopes. It is a planet of twilight, always half lost in the brightness of the star it orbits. That observational difficulty shaped the planet's scientific reputation. Mercury seemed small because it looked small. It seemed simple because very little could be seen. Before spacecraft, the human imagination had almost no surface detail to work with. Mars had markings. Jupiter had bands. Saturn had rings. Venus had mystery behind clouds. Mercury had a phase, a position, and a frustratingly tiny disk. But in science, a lack of visible drama can hide deep importance. Mercury is closest to the Sun, which means it is exposed to the strongest sunlight, strongest solar tides, and most intense solar wind of any planet. It formed in the hottest part of the planet-forming disk. It moves through the steepest part of the Sun's gravitational well. Its orbit is the most eccentric of the planets. Its surface receives the harshest space weathering environment. Its interior cooled under conditions different from any other rocky world. Everything about Mercury makes it a test case for extreme inner solar system physics. This is why Mercury matters more than its size suggests. It is not just the first planet from the Sun. It is the place where planetary science has to deal with the most intense version of several processes that affect rocky planets everywhere: tidal evolution, solar wind erosion, volatile loss, impact history, thermal contraction, magnetic field generation, and the long-term survival of surface materials under brutal irradiation. A small planet can still ask large questions. Before spacecraft arrived, the most significant early observation came from Giovanni Schiaparelli, the same astronomer who had seen the controversial canali on Mars, who reported in 1889 that Mercury appeared to rotate synchronously with its orbit, keeping the same face toward the Sun at all times, the way the Moon keeps the same face toward Earth. Schiaparelli's observation was incorrect, but it was accepted for nearly 80 years, shaping how scientists imagine Mercury's surface: one hemisphere in permanent blazing sunlight, one hemisphere in permanent icy darkness. The true picture, revealed by radar measurements in 1965, was considerably stranger. The difficulty of observing Mercury from Earth is not merely a historical inconvenience. It has lasting scientific consequences. Even today, some of the most fundamental facts about Mercury, its precise rotation rate, its surface composition, the nature of its magnetic field, were unknown or poorly constrained until spacecraft arrived, because Earth-based observations simply couldn't gather the necessary data. Mercury is, in this sense, one of the least known of the inner planets despite being relatively close and despite being visible to the naked eye. Its extreme proximity to the Sun makes it perversely difficult to study from Earth, and it will require dedicated spacecraft visits, ideally including surface landers, to fully characterize. Mercury's orbit is the most elliptical of any planet in the solar system, with an eccentricity of about 0.206. To give a sense of what this means, at perihelion, Mercury's closest approach to the Sun, it is about 46 million kilometers away. At aphelion, its farthest point, it is about 70 million kilometers away. The difference between those two distances is enormous relative to the orbit's size. Mercury's distance from the Sun varies by about 50% between its closest and farthest points. This means Mercury receives more than twice as much solar energy per unit area at perihelion than at aphelion. The Sun appears about 3 times larger in Mercury's sky at perihelion than at aphelion. The variation in heating Mercury experiences over the course of a single orbit is dramatic by any planetary standard. Mercury completes one orbit around the Sun in 87.97 Earth days, essentially 88 days. This is the shortest orbital period of any planet, and it means that while a Mercurian year is short by Earth standards, the planet's relationship between its year and its day is one of the strangest in the solar system. But before getting to that, it's worth pausing on something Mercury's orbit teaches us about the nature of space and gravity, something that until the early 20th century was simply inexplicable. Astronomers tracking Mercury's orbit over many decades noticed a small but persistent anomaly. The orbit of Mercury is not perfectly fixed in space. Every planet's elliptical orbit precesses, rotates slowly around the Sun as a result of gravitational perturbations from other planets. Mercury's orbit precesses, and most of that precession can be accounted for by the gravitational influences of Venus, Earth, Jupiter, and the other planets. But there was a residual, a small amount of precession left over after all the known gravitational influences were accounted for. About 43 arcseconds per century. That's a tiny angle, less than 1/100th of a degree per century. But it was real, it was consistent, and it couldn't be explained by Newtonian gravity applied to the known solar system. Various explanations were proposed over the decades, including the existence of an undiscovered planet closer to the Sun than Mercury, tentatively named Vulcan. Searches were conducted. Nothing was found. Then, in 1915, Albert Einstein published his general theory of relativity, a complete reformulation of gravity not as a force acting at a distance in a flat space, but as the curvature of space-time caused by mass and energy. When the predictions of general relativity were applied to Mercury's orbit, they accounted precisely for the observed 43 arcseconds of extra precession per century. Not approximately, not partially, but exactly. The anomalous precession of Mercury's orbit, which had been unexplained for decades, turned out to be a direct observational consequence of the curvature of space-time around the Sun. Mercury's orbit carries the signature of general relativity written into its motion, visible with nothing more than careful, long-term positional measurements. This was one of the first confirmations of Einstein's theory, and it remains one of the most elegant connections between a difficult abstract theory and a specific, observable, measurable fact about the solar system. Every time a spacecraft navigates to Mercury using relativistic corrections to its trajectory calculations, it is acknowledging that Einstein's reformulation of gravity was not just philosophically satisfying, but observationally necessary, demanded by the actual motion of an actual planet in an actual solar system. The relativity story is one of the reasons Mercury is more than a planetary footnote. It is easy to think of general relativity as belonging to black holes, gravitational waves, neutron stars, or the early universe. Those are the dramatic places where space-time curvature becomes extreme. Mercury is not dramatic in that way. It is a small rocky planet moving around an ordinary star. But because it orbits so close to the Sun, and because its orbit is so eccentric, the relativistic correction becomes measurable. The effect is tiny. No person standing on Mercury could look up and see relativity happening. The orbit does not visibly twist from one year to the next. It takes careful records across many decades to reveal the discrepancy. But that is exactly what makes the result powerful. A theory does not have to announce itself through spectacle to be real. Sometimes it appears as a number that refuses to fit. For decades, astronomers tried to explain the extra precession with another planet. Vulcan became a serious hypothetical object, not because anyone had seen it reliably, but because Newtonian gravity seemed to require it. Observers searched near the Sun, watching during eclipses and twilight for a small hidden world inside Mercury's orbit. Some thought they had glimpsed something. The reports did not hold up. The planet was never there. Einstein's solution was different. The missing object was not a planet. The missing ingredient was the shape of spacetime itself. The sun's mass curves spacetime, and Mercury moves through that curved geometry. The planet's orbit is not merely pulled by a force, it follows the path available in a curved gravitational landscape. That correction accounts for the stubborn 43 arcseconds per century. This gives Mercury a special place in the history of physics. It helped show that the solar system was not only a collection of planets, but also a testing ground for the deepest laws of nature. The smallest planet became evidence that gravity was stranger than Newton had imagined. Now let's talk about Mercury's rotation, because it is one of the most genuinely strange things about the planet. In 1965, Gordon Pettengill and Rolf Dice used the Arecibo radio telescope to bounce radar signals off Mercury and analyze the reflected signals. The Doppler shift in those signals revealed that Mercury was rotating, and rotating in a way that completely overturned Schiaparelli's 80-year-old observation. Mercury was not tidally locked to the sun. It was not keeping one face toward the sun permanently. Instead, it was rotating once every 58.6 days, not once per orbit of 88 days. 58.6 days. 88 days. The ratio of these two numbers, if you work it out, is almost exactly 2/3. Mercury completes exactly 2 rotations on its axis for every 3 orbits around the Sun. This relationship, 2 spins for every 3 orbits, is a specific type of gravitational resonance, called the 3-to-2 spin-orbit resonance, and it is the only example of this kind of resonance among the major bodies in the solar system. Every other tidally influenced body in the solar system has settled into a 1-to-1 resonance, keeping one face permanently toward its parent body. Mercury, under the influence of both the Sun's gravity and its highly elliptical orbit, settled into a different stable state, the 3-to-2 resonance. The reason the 3-to-2 resonance is stable rather than the simpler 1-to-1 comes down to Mercury's orbital eccentricity. In a 1-to-1 resonance, a planet's rotation rate equals its orbital speed, but for a planet in an elliptical orbit, the orbital speed is not constant. It is faster near perihelion and slower near aphelion. A planet in a 1-to-1 resonance with a significantly elliptical orbit would experience a mismatch between its constant rotation rate and its variable orbital speed, which would exert a torque on any non-spherical planet, tending to destabilize the resonance. Mercury's large eccentricity made the 1-to-1 resonance less stable, and the 3-to-2 resonance more stable, under the combined influence of the Sun's tidal forces over the billions of years of the solar system's history. The consequences of the 3-to-2 resonance for life on Mercury's surface, in the hypothetical sense, since nothing could survive there, are bizarre. A solar day on Mercury, the time from one sunrise to the next, is not 58.6 days. It is 176 Earth days, approximately 2 Mercurian years. If you were standing on Mercury's surface, you would watch the sun rise and then, bewilderingly, appear to stop, reverse direction slightly, and then resume moving forward again before finally setting. And that entire cycle would take about 88 days. The Sun's apparent reversal is a consequence of the speed of Mercury's orbital motion near perihelion temporarily exceeding the speed of its rotation, causing the Sun to appear to move backward briefly in the sky before the rotation catches up. There are specific locations on Mercury's surface, dubbed hot poles, directly beneath the Sun at perihelion, where the Sun would appear to rise, stop almost at the horizon, set again, rise once more, and then move slowly across the sky. At those locations, the Sun at perihelion hangs enormous and motionless in the sky, delivering roughly twice the solar energy that the same location receives at aphelion. This complex interplay between orbit and rotation creates the most extreme and variable solar heating environment of any planet in the solar system. with different points on Mercury's surface receiving wildly different amounts of energy depending on their location relative to the perihelion subsolar point. The 3-to-2 resonance also means Mercury is not divided into a permanent day side and night side. That old picture was wrong, but it was wrong in an interesting way. Mercury does not keep one face toward the sun, yet sunlight is not distributed evenly across its surface either. Certain longitudes receive the most intense heating again and again when Mercury is near perihelion. Other longitudes experience less extreme midday conditions. Over billions of years, this pattern has influenced temperature cycling, volatile stability, and the way surface materials respond to heat. This matters because Mercury has no atmosphere to smooth out differences. On Earth, air and ocean move heat from one region to another. On Venus, the atmosphere is so thick that the surface temperature barely changes between day and night. On Mercury, the ground is almost alone with the sun. Each patch of regolith heats and cools according to sunlight, shadow, latitude, local slope, surface material, and the long rhythm of the 176-day solar cycle. That makes Mercury a world of thermal extremes, but also of thermal geography. A crater wall facing the sun can become violently hot, while the crater floor remains colder. A polar shadow can preserve ice for billions of years while nearby sunlit ground experiences enormous heat. A surface that appears uniform in images may be divided into invisible thermal environments, each affecting chemistry and mechanical stress in different ways. The slow solar day also changes the way we should imagine time on Mercury. Sunrise is not an event that happens in minutes. It is a long transformation. Shadows crawl. The surface warms slowly but relentlessly. At local noon, heat has had weeks to penetrate the upper layers of regolith. Then the sun lowers, darkness returns, and the same ground cools through a night that lasts for months. The planet breathes thermally on a timescale completely unlike Earth. Mercury's day is therefore not just a curiosity. It is one of the engines shaping the surface. Mercury is the smallest planet in the solar system, with a diameter of about 4,879 kilometers, only slightly larger than Earth's moon. In terms of size, Mercury is actually smaller than 2 moons in the solar system. Jupiter's Ganymede and Saturn's Titan are both larger in diameter, though Mercury is considerably more massive because it's primarily made of dense metallic material rather than ice. This brings us to Mercury's most significant physical characteristic, its anomalously large iron core. By measuring Mercury's mass, its radius, and its gravitational field precisely, from spacecraft orbiting the planet, scientists have been able to construct models of the planet's interior. What those models reveal is striking. Mercury's iron core is enormous relative to the planet's total size. The core extends to about 84% of the planet's radius, meaning that if you sliced Mercury in half, the core would fill about 60% of the planet's total volume. By mass, the iron core represents approximately 70 to 80% of Mercury's total mass. For comparison, Earth's iron core represents about 32% of Earth's total mass and about 55% of Earth's radius. Mercury's core, both as a fraction of radius and as a fraction of mass, is far larger than any other planet's. It is one of the most iron-rich bodies in the solar system. The planet is, in essence, a large iron ball wrapped in a thin shell of silicate rock. Why? This is one of the fundamental open questions about Mercury, and the answer tells a story about how violent and chaotic the early solar system was. The most widely accepted explanation involves a giant impact early in Mercury's history. In this scenario, Mercury originally formed with a more normal composition, a silicate mantle of normal proportions surrounding an iron core. But early in the solar system's history, before the planets had settled into their current orbits, a large object, possibly a protoplanet roughly a third of Mercury's mass, collided with Mercury at high velocity. The impactor struck and stripped away most of Mercury's silicate mantle, preferentially ejecting the lighter rocky material into space and leaving behind the dense iron core with only a thin silicate coating. The lost material may have been swept up by the sun or distributed through the inner solar system, leaving Mercury as the iron-dominated world we see today. This giant impact hypothesis has the advantage of explaining the large core straightforwardly, and it is consistent with the general picture of early solar system violence, the same period that is thought to have produced Earth's moon through a similar impact mechanism. But it has challenges. The physical details of how a giant impact could produce the specific composition observed, rather than completely disrupting Mercury, require specific conditions that modelers are still working out. Alternative hypotheses exist. Mercury may have formed from unusual starting material enriched in iron relative to the average solar system composition, possibly because the intense early sun preferentially drove lighter silicate vapor away from the innermost part of the disk. Or Mercury may have lost much of its silicate mantle through a process of large-scale evaporation in the intense heat close to the young sun. Each hypothesis has observational tests, and current and future missions are designed to discriminate between them by precisely measuring Mercury's bulk composition and the chemistry of its surface. What is clear is that Mercury's interior structure is unlike any other rocky planet in the solar system, and understanding why is directly relevant to understanding the diversity of planetary compositions both within our solar system and around other stars. Surface gravity on Mercury is only about 38% of Earth's, identical, as it happens, to the surface gravity on Mars. If you could stand on Mercury, which you cannot, for reasons we'll come to, you would weigh the same as you would on Mars, despite Mercury being far smaller in size. The higher density of Mercury's iron-dominated composition partially compensates for its smaller radius in determining the surface gravity felt at the top of that composition. A spacecraft needs to reach Mercury's escape velocity to leave its surface, about 4.3 kilometers per second. This is low enough that any molecule moving fast enough in the heated lower atmosphere would escape fairly readily, which is one of the reasons Mercury has essentially no atmosphere. But let's spend some time with the temperatures on Mercury's surface, because they represent the most extreme range of any planet in the solar system, more extreme even than the absolute surface temperatures of outer solar system bodies, because Mercury's range from maximum to minimum is nearly 700 degrees. The day side of Mercury, under direct sunlight without any atmosphere to moderate temperatures, can reach about 430 degrees Celsius at its hottest points. Not the hottest in the solar system. Venus, with its enormous heat-trapping greenhouse atmosphere, maintains a higher average surface temperature. But on Venus, the heat is distributed evenly across the planet by the thick atmosphere. On Mercury, the heat is concentrated on the directly sunlit regions, particularly near the subsolar point at perihelion, while the night side experiences something entirely different. The night side of Mercury, without any atmosphere to retain heat during the long night, cools to approximately minus 180 degrees Celsius. The combination of 430 degrees on one side and minus 180 on the other gives Mercury a surface temperature range of about 610 degrees Celsius across its surface at any given time, the greatest range of any planet. On Earth, the difference between the hottest and coldest surface temperatures ever recorded is only about 170 degrees. Mercury's range is nearly 4 times larger. Even at a single location on Mercury's surface, the temperature swings enormously over the course of the long solar day. The same patch of ground that experiences 430 degrees during the midday sun will plunge to minus 180 degrees during the long Mercurian night, a swing of over 600 degrees in the course of a single day, a day that lasts 176 Earth days. No material in conventional engineering can accommodate such temperature swings without significant stress. Rock itself expands when hot and contracts when cold, and the scale of Mercury's temperature swings means that surface rocks are undergoing much larger thermal cycling than rocks on any other rocky planet. What would it actually feel like to stand on Mercury's surface? Leaving aside the complete absence of breathable air and the instant death that would cause, the physical experience would be defined primarily by extremes. In daylight, on the sunlit hemisphere, the sun would appear between about 1.5 and 3 times larger than it appears from Earth, depending on whether Mercury is near aphelion or perihelion. Near perihelion, at the hot poles, the sun would appear enormous in the sky, swollen, blinding, close. The solar disk would subtend nearly 3 times the angle it subtends from Earth, making it appear 9 times brighter per unit area. The solar constant at Mercury's perihelion, the total solar energy per unit area, is about 11 times higher than at Earth's distance from the Sun. The ground beneath your feet would be deep gray and brown. Mercury's surface is one of the darkest in the solar system, reflecting only about 12% of incoming sunlight. It is darker than charcoal, darker than fresh asphalt. This low reflectivity is partly due to the dark minerals in Mercury's surface rock and partly due to space weathering, the long-term modification of surface minerals by solar wind bombardment and micrometeorite impacts, which creates a coating of fine, dark nanophase iron particles on mineral grains, darkening the surface over billions of years. The landscape would be lunar in character, craters of all sizes in all directions, the larger ones with central peaks and terraced walls, the smaller ones overlapping and partially buried. The horizon would be close. Mercury's small size means the horizon is only about 2.5 kilometers away, compared to about 5 kilometers on Earth. The curvature of the planet is sharper, and the horizon is nearer. Beyond it, the same cratered terrain continues, unchanging. The sky overhead would be black even in full daylight. Without an atmosphere to scatter sunlight, Mercury has no blue sky, no haze, no twilight. The sun blazes from a black sky. Stars are visible alongside the blazing sun if you look in a direction away from it. The black sky, the enormous sun, the gray and brown cratered terrain, the absolute silence. Mercury's surface would be simultaneously among the most dramatic and most desolate environments imaginable. In the permanently shadowed craters near the poles, the scene is entirely different. Without direct sunlight, temperatures sit permanently near minus 180 degrees, cold enough that any water ice delivered by comets or asteroids over billions of years would remain frozen and stable essentially indefinitely. The darkness is absolute. No sunlight reaches these floors, no starlight bright enough to see by. The ice lies in total darkness, preserved for geological ages, unknown to any observer until radar measurements first suggested its presence from Earth in the 1990s. Mercury, like the Moon, has been collecting impact craters for most of the solar system's history, and without the resurfacing processes, oceans, tectonics, weather, that erase craters on more geologically active planets, Mercury's surface preserves a record stretching back billions of years. Large, ancient craters cover much of the planet's surface, many of them modified by later impacts or partially flooded by volcanic lava that erupted in Mercury's earlier, more geologically active past. The most dramatic surface feature on Mercury is the Caloris Basin, an impact crater about 1,550 kilometers in diameter, roughly a third the diameter of Mercury itself. Caloris was formed by the impact of a large asteroid or comet early in Mercury's history, an impact so energetic that it not only excavated the enormous basin, but sent seismic waves propagating through the entire planet. On the side of Mercury directly opposite the calorous impact point, the antipodal point, the converging seismic waves from the impact arrived simultaneously from all directions and disrupted the surface in a region of chaotic, broken, jumbled terrain called weird terrain, or more formally, chaotic terrain. This antipodal disruption is direct physical evidence of how powerful the calorous impact was, powerful enough that its seismic signature propagated through the entire bulk of the planet and expressed itself on the opposite hemisphere as a geological upheaval. Calorus is one of the largest impact basins in the solar system, comparable in scale to Mare Imbrium on the Moon and Hellas Planitia on Mars. The interior of the basin has been partially flooded by later volcanic eruptions, creating relatively smooth plains within the enormous ring of mountains that marks the basin's rim. Outside the basin, ejected material from the impact created a complex terrain of hummocks, ridges, and secondary craters extending for hundreds of kilometers. Surrounding the ancient, heavily cratered terrain are regions of younger, smoother volcanic plains, intercrater plains, and smooth plains that record the period when Mercury was still geologically active, still erupting lavas that flooded lower-lying regions and partially buried older craters, resurfacing large portions of the planet before Mercury's interior cooled enough that volcanism ceased. Based on crater counting and compositional analysis from MESSENGER, the volcanic plains appear to have formed primarily during the first billion to 2 billion years of Mercury's history, suggesting that Mercury's geological activity was front-loaded, intense early, and then declining rapidly as the small planet lost its internal heat. One feature visible in MESSENGER's detailed images stands out as uniquely Mercurian and still incompletely understood: the lobate scarps. Mercury is crisscrossed by long, sinuous cliffs called lobate scarps or rupees, some of them hundreds of kilometers long and up to 3 kilometers high. These scarps are the preserved geological record of Mercury's global contraction over its history. As Mercury's interior cooled, the iron core solidified and the planet shrank. The reduction in volume, estimated at up to 7 kilometers in radius, caused the surface to buckle, with large sections of crust being thrust over adjacent sections along thrust faults, creating the lobate scarps visible today. This global contraction is unique among the rocky planets in the solar system in its scale and clarity. Earth's tectonic activity complicates and obscures similar processes. Mars shows some contractional features, but its geological history is more complex. The Moon shows some contraction, but on a smaller scale. Mercury, with its enormous iron core and its lack of resurfacing processes, has preserved the evidence of planetary-scale shrinkage with a clarity impossible on more geologically active worlds. And the scarps are not all ancient. Some MESSENGER observations suggest that at least some lobate scarps are geologically young, meaning that Mercury's cooling and contraction may still be occurring, albeit slowly. The planet may still be getting slightly smaller. Beyond the scarps, perhaps the most unexpected discovery of the MESSENGER mission was a type of surface feature not seen anywhere else in the solar system: hollows. These are irregular, shallow, flat-floored depressions, typically tens to hundreds of meters deep and ranging from a few meters to a few kilometers across, found primarily on the floors and walls of some craters. They appear bright relative to the surrounding terrain and show no evidence of impact or volcanic origin. They appear to be actively forming. Some MESSENGER analyses suggested that fresh hollows might be forming on timescales short enough to be geologically recent or even ongoing. The current best explanation for the hollows involves the sublimation of volatile materials. Mercury was thought, for most of its observational history, to be highly depleted in volatile elements and compounds that vaporize at relatively low temperatures, which should have been driven off by the intense solar heating Mercury experiences. But MESSENGER found, surprisingly, significant quantities of volatile elements in Mercury's surface material, including sulfur, sodium, potassium, and chlorine, in quantities much higher than expected given the temperatures at which these materials should evaporate. If patches of volatile-rich material are exposed at the surface, perhaps by a crater excavating previously buried material, the intense solar heating could cause those volatiles to sublimate, leaving behind the irregular, shallow depressions observed as hollows. This interpretation, if correct, has implications for Mercury's entire history and composition. It would mean that Mercury did not lose its volatile elements as thoroughly as had been assumed, which in turn constrains the models of Mercury's formation and the environment in which it formed. The hollows are small features by planetary standards, but they are scientifically significant out of proportion to their size. There is another part of Mercury's story that is easy to miss because it is not one single spectacular feature. It is the surface chemistry. For a long time, scientists expected Mercury to be depleted in volatile elements. That expectation seemed logical. Mercury formed close to the Sun, where temperatures in the early solar nebula were high. It then spent billions of years exposed to intense sunlight and solar wind. A small, hot, airless planet should have lost much of its sodium, potassium, sulfur, chlorine, and other elements that vaporize or move more easily than refractory rock-forming minerals. If Mercury was produced by a giant impact that stripped away much of its mantle, the expectation became even stronger. A violent, high-energy event should have removed volatiles even more efficiently. MESSENGER challenged that picture. Its instruments found that Mercury's surface contains more volatile material than simple models predicted. Sulfur is especially important because it can tell scientists about the chemical environment in which Mercury formed. The presence of substantial sulfur suggests that Mercury may have formed under highly reducing conditions, a chemical environment in which oxygen was less available to bind with metals and silicates. This is different from the conditions inferred for Earth, the Moon, and Mars. Mercury may not just be an ordinary rocky planet that lost its mantle. It may have formed from chemically unusual building blocks in a distinct region of the early disk. The surface also contains relatively little iron in the silicate portion, despite the planet as a whole being extremely iron-rich. This is counterintuitive. Mercury's bulk density tells us the planet is dominated by iron, but its surface does not look like a simple iron-rich crust. That means the iron is concentrated deep inside the planet, in the enormous core, while the outer rocky shell has its own distinct chemistry. This division between bulk composition and surface composition is one reason Mercury is so difficult to explain with a single simple formation story. Carbon may also play an important role. Some studies have suggested that Mercury's dark surface may contain carbon-rich material, possibly in the form of graphite. If Mercury once had a global magma ocean early in its history, graphite could have floated to the surface as the magma ocean crystallized, forming a primordial flotation crust. Later impacts and volcanic activity would have broken, buried, mixed, and re-exposed that carbon-rich material. If true, this would make Mercury's dark color not merely the product of space weathering, but a clue to the planet's earliest differentiation. This possibility is striking because graphite is familiar to us as the material in pencil lead, but on Mercury, it may be a planetary-scale remnant of the first crust. A dark ancient skin formed when the planet was molten, later shattered by impacts and buried under volcanic plains, then exposed again in certain terrains. The idea is still being investigated, but it captures something important about Mercury. Even its color may be telling a deep interior story. The chemistry also matters for the hollows. If volatile-rich minerals are present in the crust, then sunlight and space exposure can remove them when they are brought to the surface. Hollows may be places where Mercury is literally losing ingredients from its rocks, not through flowing water or wind erosion, but through the direct escape of unstable materials into space. A hollow is therefore not just a depression. It is a chemical wound, a place where the surface composition is changing under the extreme conditions near the sun. This makes Mercury feel less like a dead moon and more like a world with active surface chemistry. The processes are not biological, not atmospheric, not watery. They are mineralogical and solar-driven. But they are real. They reshape small regions of the surface and preserve information about the ingredients from which the innermost planet was built. One of the most counterintuitive facts about Mercury is the presence of water ice. Mercury is the closest planet to the Sun. Its dayside surface temperatures reach 430 degrees Celsius, hot enough to melt tin, hot enough to boil several metals. And yet, at Mercury's poles, in the permanently shadowed interiors of craters, radar observations from Earth and detailed measurements from MESSENGER have confirmed the presence of substantial deposits of water ice. The polar ice exists because of Mercury's near-zero axial tilt. Mercury's axis is tilted only about 0.02 of a degree from perpendicular to its orbital plane, the smallest axial tilt of any planet. On Earth, the axial tilt of 23.5 degrees means that the poles receive different amounts of sunlight through the year, and the sun sometimes rises above even the highest latitudes. On Mercury, the near-perfect alignment of the rotation axis with the orbital axis means that the sun never rises above the horizon at the poles. Craters near Mercury's poles have floors that are permanently in shadow, never receiving direct sunlight. In those permanently shadowed regions, temperatures can remain permanently below -170 degrees Celsius, cold enough to preserve ice essentially indefinitely. The ice at Mercury's poles is substantial. MESSENGER estimated that the total mass of ice in Mercury's polar deposits could be comparable to the ice in some of the mid-sized glaciers on Earth, not a trivial quantity. This ice is thought to have been delivered to Mercury over geological time by comets and asteroid impacts. Comets are largely composed of water ice, and when they impact Mercury, the water released can migrate across the surface toward the poles, where it is stable in the permanently shadowed craters. Over billions of years, this gradual delivery and concentration of cometary water at the poles has built up the deposits observed today. The polar ice is covered in some regions by a thin, dark layer of material, organic compounds, possibly delivered along with the water by the same cometary or asteroid impacts, or produced by radiation processing of the surface in the shadowed regions. This dark layer acts as an insulating blanket, protecting the ice beneath from the heat that diffuses in from the adjacent sunlit terrain. The discovery of water ice at Mercury's poles has implications beyond just Mercury. It demonstrates that even the most hostile, sun-baked bodies in the solar system can preserve volatile materials if the local geometry creates protected pockets away from direct sunlight. The same physics applies at the Moon's poles, where water ice has also been detected in permanently shadowed craters. And the existence of that lunar ice is one of the reasons current human lunar exploration programs are targeting polar regions. Mercury's polar ice is both a scientific curiosity and a demonstration of a physical principle with broader application. The absence of a real atmosphere also means there is no sound as human beings know it. A rockfall on Mercury would not echo across a canyon. An impact would not boom through the air. There is no wind to lift dust into storms, no rain to round boulders, no frost forming on open plains outside the polar traps, no cloud passing between the ground and the sun. Events still happen, but they happen in silence. Dust is thrown by impacts, then falls back without drifting. Micrometeorites strike the surface at high speed, melt tiny grains, and leave microscopic glassy deposits. Solar wind particles hit the regolith directly, altering chemistry atom by atom. This direct exposure to space is part of what makes Mercury's surface scientifically useful. On Earth, the surface is constantly recycled by weather, oceans, biology, and plate tectonics. On Mercury, the surface preserves ancient scars because there is almost nothing to erase them. A crater can remain recognizable for billions of years unless later impacts or volcanic flooding modify it. A cliff produced by planetary contraction can stand for ages. A basin formed by a colossal impact becomes a permanent record of one violent moment in deep time. But preservation is not the same as stillness. The surface is also being slowly changed by space weathering. Micrometeorites darken and garden the regolith. Charged particles from the sun implant atoms and knock others loose. Thermal cycling cracks and stresses rocks. Volatile-rich patches may degrade into hollows. Mercury is quiet in the human sense, but it is not untouched. Its environment is constantly working on the surface, just through processes that are subtle, particle scale, and slow. That difference is important for storytelling and for science. Mercury does not have weather. It has exposure. It does not have erosion by air and water. It has erosion by sunlight, impact dust, charged particles, and time. Mercury's magnetic field is one of its most puzzling features. Magnetic fields on rocky planets are generated by the same basic process as on Earth: the movement of electrically conducting fluid, typically molten iron, within the planet's core. This process, the geodynamo, requires a liquid outer core that is convecting, moving in response to heat flowing from the hot interior outward to the cooler mantle. On Earth, the inner core is solid, the outer core is liquid, and the temperature difference between them drives vigorous convection that generates a substantial magnetic field. On Mars, the core cooled and solidified early in the planet's history, shutting down the dynamo and leaving behind only fossil magnetism in the ancient crust. On Venus, the slow rotation and possibly small temperature contrast between core and mantle has apparently failed to generate a detectable field. Mercury, being smaller than Earth and closer to the Sun, should have cooled faster than Earth, losing its internal heat more quickly and solidifying its core earlier. By straightforward reasoning, Mercury should not have a global magnetic field. Its core should be too cool to sustain convection. And indeed, before Mariner 10 flew past Mercury in 1974, most planetary scientists expected to find no magnetic field. Mariner 10 found one. A small one. Mercury's magnetic field is only about 1% as strong as Earth's, but a genuine, global, dipole field, oriented similarly to Earth's, and clearly indicating an active interior dynamo rather than fossil magnetism. This was one of the surprising discoveries of the Mariner 10 mission, and it has remained puzzling ever since. How does Mercury maintain an active dynamo? The leading hypothesis draws on the idea that the planet's core is not entirely solid. Mercury's large iron core, under the pressures existing within a planet of Mercury's size, can maintain a liquid outer layer if the melting point of the iron in the outer core is sufficiently reduced by the presence of light elements, sulfur, silicon, or other materials, dissolved in the iron. If light elements are present in sufficient concentration in the outer portions of Mercury's core, they can lower the melting point enough to keep the outer core liquid, even though Mercury's small size would otherwise predict complete solidification. Messenger's detailed gravity measurements helped constrain the interior model, showing that Mercury's core is indeed partially liquid, with a solid inner core surrounded by a liquid outer core. The presence of a liquid outer core is consistent with the ongoing dynamo. But there's another puzzle about Mercury's magnetic field. It's significantly weaker than models would predict for a dynamo operating in a core of Mercury's size. The field is also measurably offset from the planet's center. The magnetic dipole is displaced about 480 kilometers northward from Mercury's geometric center. The offset produces a measurable north-south asymmetry in the field, which was clearly detected by MESSENGER's magnetometer instruments during the mission's orbital phase. Various explanations have been proposed for the weak field and the north-south asymmetry. One involves a layer of iron sulfide or other low-melting point material above the outer core that partially shields the dynamo's field from reaching the surface. Another involves the specific geometry of convection and Mercury's core being influenced by the north-south asymmetry in solar heating. The planet receives significantly more solar energy at low latitudes than at high latitudes, and this heat input from the surface might perturb the convection patterns within the core in a way that produces the observed asymmetric field. The Bepi-Colombo mission, currently en route to Mercury, is equipped with more sensitive magnetic field instruments than MESSENGER and is expected to characterize the field in far greater detail, potentially distinguishing between these hypotheses. The mere existence of Mercury's magnetic field is one of the reasons planetary scientists find the inner solar system's smallest planet so scientifically rich. A field that shouldn't exist, with a structure that current models struggle to fully reproduce, in a planet with an interior we've only begun to constrain. Mercury's magnetic field is a genuinely open scientific problem. Mercury's magnetosphere is tiny compared with Earth's, but it is intense in its own way. Earth's magnetic field creates a vast protective cavity around the planet, with the solar wind mostly deflected far above the atmosphere. Mercury's field is much weaker, and Mercury sits much closer to the Sun, where the solar wind is stronger. The result is a small, compressed, highly dynamic magnetosphere that can change rapidly as solar conditions change. At times, the solar wind can push Mercury's magnetosphere so hard that charged particles gain direct access to the surface. Magnetic reconnection, the process in which magnetic field lines break and reconnect, releasing energy, can occur efficiently at Mercury. This can funnel solar wind plasma down along magnetic field lines toward the surface, sputtering atoms from the regolith into the exosphere and changing the surface chemistry. NASA summaries sometimes describe these events as magnetic tornadoes, not because they are air vortices, but because twisted magnetic structures can guide energetic particles downward. This makes Mercury a natural laboratory for star-planet interaction. Many exoplanets orbit close to their stars, exposed to stellar winds far stronger than Earth's environment. Some may have weak magnetic fields, or none at all. Mercury gives scientists a nearby example of how a small rocky planet with a weak magnetic shield interacts directly with its star. The planet is not protected from space in the way Earth is. It is coupled to the Sun. The magnetosphere also connects the interior to the surface. A field generated deep in the core controls where solar wind particles reach the surface. Those particles then release atoms into the exosphere. The exosphere changes with Mercury's orbit and with solar activity. The surface records the cumulative effects of bombardment. One weak magnetic field links core dynamics, space weather, surface chemistry, and the planet's faint envelope of atoms. That is why Bepi-Colombo's two-orbiter design matters. One orbiter will focus more on the planet itself, surface, composition, gravity, topography. The other will focus on the magnetosphere and space environment. Mercury cannot be fully understood by separating those subjects. The interior, the surface, the exosphere, and the solar wind are parts of one connected system. Mercury's near absence of atmosphere is one of its defining features, and it shapes nearly everything about the planet's environment. It is not quite accurate to say Mercury has no atmosphere. It has what is called an exosphere, an extremely tenuous envelope of gas where the density of atoms is so low that collisions between them are essentially negligible. In a true atmosphere, gas molecules collide so frequently that they behave collectively, maintaining pressure and temperature and enabling weather. In Mercury's exosphere, individual atoms travel in ballistic trajectories, essentially orbiting Mercury in arcs that may bring them back to the surface or send them into space, with no significant collisions with other atoms along the way. The atoms that make up Mercury's exosphere come from several sources. Solar wind particles, ions of hydrogen, helium, and heavier elements traveling outward from the Sun, strike Mercury's surface and are either absorbed by surface minerals or implanted briefly into the exosphere. The intense solar radiation also drives photon-stimulated desorption. Ultraviolet photons striking the surface can knock atoms loose from mineral grains, adding them to the exosphere. Meteorite impacts vaporize surface material directly, adding it to the exosphere. And some volatile materials, such as sodium and potassium, can thermally dwarf from the hot dayside surface under direct solar heating. The result is an exosphere dominated by sodium, oxygen, hydrogen, helium, calcium, and a variety of other species, each with its own distribution and dynamics driven by the different processes producing and removing it. Sodium is particularly prominent and produces a bright yellow emission visible in specialized telescopes. Some sodium escapes Mercury entirely, forming a comet-like tail trailing behind the planet away from the Sun, a sodium tail that can extend for millions of kilometers into space and has been photographed from Earth. Mercury's exosphere is continuously being created and continuously being lost to space. The solar wind can strip exospheric atoms away from Mercury, carrying them outward. Atoms that don't escape recycle back to the surface. The whole system is a dynamic, constantly churning exchange between the surface, the exosphere, and space, driven by solar radiation and the solar wind. This has practical implications for understanding how Mercury's surface evolves. The space weathering process, the modification of surface minerals by solar wind bombardment, micrometeorite impacts, and photon irradiation, is far more intense on Mercury than on any other planet, because Mercury receives solar energy and solar wind intensity many times higher than the outer planets. The surface of Mercury has been processed by these effects for the entire history of the solar system, and the resulting chemistry is different from what you'd find on Mars or the Moon. The sodium tail and the exosphere have been studied from Earth for decades, providing the primary means of studying Mercury's surface chemistry remotely before spacecraft arrived. Variations in the sodium tail brightness over time, correlated with Mercury's position in its orbit, revealed something important. The sodium tail intensity peaks near Mercury's perihelion, when solar radiation is most intense. This confirmed that solar heating is one of the primary drivers of the exosphere's dynamics, and that Mercury's extreme proximity to the Sun is directly responsible for the vigor of its exospheric processes. The engineering problem of Mercury exploration is also part of the science, because it explains why we know so little compared with nearby worlds. Mars is difficult, but spacecraft can aerobrake in its atmosphere, use solar power effectively, and communicate with Earth at manageable distances. Venus is hostile at the surface, but it is relatively easy to reach and has a thick atmosphere that can slow spacecraft naturally. Mercury combines several difficulties at once. It is close to the Sun, so spacecraft must survive high solar heating. It has almost no atmosphere, so there is no easy aerobraking. It is small, so its gravity is weak. And any spacecraft falling inward from Earth's orbit gains speed as it descends toward the Sun, arriving at Mercury with too much energy to be captured easily. This is why trajectories to Mercury are so strange. A direct path is not enough. The spacecraft must spend years using planetary flybys and careful engine burns to remove orbital energy. It must repeatedly pass near planets not to speed up as outer solar system missions often do, but to slow down relative to the Sun. The path can look wasteful on a map: loops around the inner solar system, repeated encounters with Venus and Mercury, but energetically it is elegant. The spacecraft is trading time for fuel. Mariner 10 used Venus once to reach Mercury for flybys. Messenger used Earth, Venus, and Mercury repeatedly before it could enter orbit. Bepi-Colombo uses an even longer choreography, including Earth, Venus, and multiple Mercury flybys, before Mercury orbit insertion. This is not because mission designers enjoy complexity. It is because the Sun dominates everything near Mercury. To orbit the innermost planet, a spacecraft must first solve the problem of the Sun. Thermal design is just as difficult. A spacecraft near Mercury receives many times the solar energy it would receive near Earth. Instruments must be protected from heat while still looking at the planet. Solar panels must be angled carefully so they receive enough light for power, but not so much that they overheat. Radiators must dump internal heat into space while avoiding the intense glare from both the Sun and Mercury's hot surface. The spacecraft must operate in an environment where heat comes from multiple directions: direct sunlight, reflected sunlight, and infrared radiation from the planet itself. Messenger used a large ceramic fabric sunshade to keep its instruments in shadow. Bepi-Colombo uses advanced thermal protection, coatings, radiators, and careful spacecraft orientation to survive its cruise and eventual orbital operations. These engineering details are not separate from the story. They are the reason Mercury remains rare in spacecraft history. It is not far away in the outer solar system, but it is hard to hold on to. The same is true for landing. A lander at Mercury would face radically different challenges depending on where it touches down. Near the equator, the temperature cycle is brutal. Months of heating, months of cooling, and surface temperatures that can exceed the limits of ordinary electronics. Near the poles, conditions may be colder and more stable in shadowed regions, but power becomes difficult because sunlight is low or absent. A lander targeting polar ice would have to operate in deep cold and darkness, possibly communicating with an orbiter overhead while using limited power. A lander targeting hollows would need to survive strong sunlight and intense thermal stress. This makes every proposed Mercury surface mission a compromise between scientific value and survival. The most interesting places may not be the easiest places to land. The safest places may not answer the hardest questions. A polar lander could study ice, dark material, and volatile delivery. A mid-latitude lander could study hollows and surface chemistry. A high-resolution orbital mission can map broadly but cannot touch, drill, date, or sample directly. A sample return mission would be even harder. The spacecraft would need to reach Mercury, land or collect material, launch from the surface or collect from orbit if an impact plume method were used, escape Mercury's gravity, climb back outward against the Sun's gravity, and return the sample safely to Earth. The scientific reward would be enormous, but the energy cost is severe. This difficulty is one reason Mercury remains underexplored despite its importance. It is not ignored because it is uninteresting. It is ignored because it is hard. The first spacecraft to visit Mercury was Mariner 10, launched in November 1973 and arriving at Mercury in March 1974. Mariner 10 made 3 flybys of Mercury in March 1974, September 1974, and March 1975, before its attitude control fuel was exhausted and the mission ended. During those flybys, Mariner 10 mapped approximately 45% of Mercury's surface, discovered the magnetic field, measured the exospheric composition, and returned about 4,000 photographs showing a moon-like landscape of craters, plains, and scarps. Mariner 10's trajectory to Mercury was itself an achievement. It was the first spacecraft to use a planetary gravitational assist from one planet to reach another, using Venus's gravity to bend its trajectory toward Mercury, a maneuver that established the technique later used by Voyager, Galileo, Cassini, and many other missions. The Venus gravity assist reduced the fuel required to reach Mercury by an enormous factor, making the mission possible with the technology of the early 1970s. The mission's success was partly due to a fortunate coincidence. On each of Mariner 10's 3 Mercury flybys, Mercury's orbital position relative to the spacecraft was almost identical, because Mariner 10's orbital period around the Sun happened to be almost exactly twice Mercury's orbital period. This meant that between flybys, Mercury completed almost exactly 2 orbits, while Mariner 10 completed almost exactly 1, and they met at nearly the same point in space each time. The consequence was that each flyby illuminated essentially the same hemisphere of Mercury, leaving the other hemisphere completely unobserved. After 3 flybys covering 45% of the surface, Mariner 10 ran out of fuel and the mission ended, with the same 45% mapped and the other 55% unknown. That unknown 55% remained unmapped for nearly 4 decades, until Messenger, short for Mercury surface, space environment, geochemistry, and ranging, launched in August 2004. The journey to Mercury was not direct. To reach Mercury's orbit with enough fuel remaining to break into orbit rather than simply fly past, Messenger required a complex series of gravitational assists. 1 Earth flyby in August 2005, 2 Venus flybys in October 2006 and June 2007, and 3 Mercury flybys in January 2008, October 2008, and September 2009, before finally entering orbit around Mercury in March 2011, 6.5 years after launch, and after traveling nearly 8 billion kilometers in total to cover the 177 million kilometers from Earth to Mercury. Why such a tortuous path? The problem is energy. Mercury is close to the Sun, and anything moving toward the inner solar system naturally speeds up as it falls inward under the Sun's gravity. A spacecraft aimed directly at Mercury from Earth would arrive moving far too fast to be captured by Mercury's weak gravity. It would need to fire enormous amounts of rocket fuel to slow down enough. The complex flyby sequence was designed to shed the excess velocity progressively, using the gravity of Earth, Venus, and Mercury itself to lose kinetic energy over multiple encounters, arriving at Mercury slow enough that a manageable amount of rocket fuel could complete the orbital insertion. Once in orbit, Messenger spent 4 years studying Mercury in extraordinary detail. It mapped the entire surface, not just the 45% Mariner 10 had seen. It measured the composition of the surface using X-ray, gamma-ray, and neutron spectrometers, revealing the unexpected abundance of volatile elements. It measured the magnetic field with precision sufficient to characterize its offset and asymmetry. It studied the exosphere's composition and dynamics through multiple instruments. It measured the topography of the entire planet with a laser altimeter, constructing the first global topographic map. It measured the gravity field with sufficient precision to constrain models of the interior structure. And its cameras documented the surface at resolutions far exceeding anything from Mariner 10, revealing the hollows, the detailed structure of the scarps, the evidence for recent geological activity, and hundreds of other features. At the end of its mission, Messenger had exhausted its propellant. With no fuel remaining for orbital maneuvering, the spacecraft's orbit gradually decayed under the influence of solar gravity perturbations. On April 30th, 2015, Messenger impacted Mercury's surface at approximately 3.9 kilometers per second, creating a small impact crater on the northern hemisphere that commemorates the mission's end. Unlike some spacecraft disposed of more ceremonially, Messenger's impact added a modest final piece of geological data, a small, fresh crater on the planet it had spent 4 years studying. The scientific legacy of Messenger is enormous. The mission fundamentally transformed our understanding of Mercury across nearly every domain: surface geology, composition, magnetic field, exosphere, interior structure, and evolutionary history. It resolved some questions definitively and raised new ones that will require future missions to answer. The Messenger dataset will be analyzed by scientists for decades. The next Mercury mission is already on its way. Bepi-Colombo, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency, launched in October 2018 and is currently making its own complex, multi-flyby journey to Mercury, planned to enter Mercury orbit in late 2026. Bepi-Colombo consists of 2 separate science orbiters that will separate and orbit Mercury independently after Mercury orbit insertion. ESA's Mercury Planetary Orbiter, focused on the surface and interior, and JAXA's Mercury Magnetospheric Orbiter, focused on the magnetic field, magnetosphere, and exosphere. Together, they will carry more than 80 scientific instruments, far exceeding the capabilities of Messenger in several specific areas. Bepi-Colombo will make magnetic field measurements of unprecedented precision, potentially distinguishing between the different hypotheses for Mercury's weak, offset field. It will study the exosphere with higher sensitivity than any previous mission. It will image selected portions of the surface at higher resolution than Messenger and with additional wavelength coverage. It will measure the thermal emission from the surface, helping to understand the near-surface temperature distribution and the properties of the upper layer of regolith. And it will measure the gravity field with even greater precision than Messenger, further constraining the interior structure models. Bepi-Colombo's Mercury orbit insertion, now planned for late 2026 after its final Mercury flyby in January 2025, will mark the beginning of a new chapter of Mercury science, building on everything Messenger discovered and pushing further into the questions that the previous mission could not fully answer. Bepi-Colombo's cruise has already added to the story, even before full orbital science begins. Its flybys have returned images of regions seen under unusual lighting, including views near the North Pole and the boundary between day and night. Those images are not the mission's main science phase, but they remind us that Mercury still has surprises in geometry alone. A different angle of sunlight can make old terrain look new. A shadowed crater rim can reveal the cold traps that preserve ice. A low-altitude pass can sharpen the sense of scale on a planet that is often reduced to diagrams. The delayed orbit insertion also illustrates something often missed in discussions of spacecraft exploration. Reaching Mercury is not simply flying inward toward the Sun. It is one of the most difficult navigational tasks in planetary science. The spacecraft must lose solar orbital energy, not gain it. It must survive increasing heat and radiation. It must use repeated flybys to reshape its trajectory. A mission to Mercury is a long act of braking in a gravity well, not a short fall toward an easy target. Once Bepi-Colombo separates into its 2 orbiters, the mission will allow a kind of coordinated study that Messenger could not perform. Measurements of the magnetic field, particles, exosphere, surface composition, thermal emission, and gravity can be combined across instruments and altitudes. This matters because Mercury's processes are coupled. A change in solar wind conditions can affect the exosphere. A magnetic field measurement can inform interior models. A surface composition measurement can test formation theories. A thermal map can help explain volatile stability and hollow formation. The more pieces are measured together, the less Mercury has to be interpreted through isolated clues. The mission is also important because it arrives after Messenger has already defined the questions. Mariner 10 revealed Mercury was strange. Messenger showed how strange. Bepi-Colombo is designed to ask why. Mercury's formation and evolutionary history is a subject of active scientific debate, and the resolution of that debate will have implications reaching well beyond Mercury itself. The giant impact hypothesis for Mercury's large core, the idea that a massive impactor stripped away most of Mercury's silicate mantle early in its history, has been the dominant explanation for several decades. It has the advantage of explaining the anomalously large core in a straightforward way, and it fits within the general picture of a chaotic early solar system in which large impacts were common and could dramatically alter the composition and structure of forming planets. The timeline of events in this hypothesis is roughly as follows. Mercury initially accretes from the swirling disk of solid particles surrounding the young sun, building up a roughly normal rocky planet with a silicate mantle of proportions similar to Earth's and a metallic iron core. Then, in the period of intense bombardment that characterized the first few 100 million years of the solar system, the same period that created the large impact basins on the Moon and that is thought to have formed Earth's moon through a giant impact, a large protoplanet, estimated to have been perhaps a quarter to a third of Mercury's current mass, collides with Mercury at high velocity. The impactor's energy is sufficient to eject most of Mercury's silicate mantle into space. The lighter silicate material, having lower density and being on the outer portion of the planet, is disproportionately lost. The denser iron from both the impactor's core and Mercury's original core survives the collision and reconcentrates in the central mass. The planet that recoalesces from the collision debris is therefore dramatically enriched in iron, which is exactly what we observe. The physical details of this collision have been modeled extensively using smooth particle hydrodynamics simulations, computer simulations that model both the impactor and target as large numbers of fluid particles interacting gravitationally and through pressure forces. These simulations show that a range of impact conditions can produce a Mercury-like outcome: large iron core, thin silicate mantle. The challenge is that they also produce specific predictions about the composition of the remaining silicate layer that can be tested against observations, and the messenger observations of Mercury's surface chemistry have provided those tests. Messenger's measurements created a problem for the simple version of this hypothesis. If a giant impact stripped Mercury's mantle, you'd expect the remaining surface to be severely depleted in volatile elements. The intense heat generated by a massive impact should have vaporized any volatiles present, and the solar proximity should have driven off whatever remained. Instead, Messenger found significant abundances of sulfur, potassium, sodium, chlorine, and other volatile elements in Mercury's surface material, abundances inconsistent with the planet having been thoroughly heated by a major impact. The abundances of volatile elements are comparable to, and in some cases higher than, those found on the Moon or Mars, two bodies whose formation models predict much less heating than Mercury would have experienced in a giant impact. This has prompted revisions to the giant impact hypothesis. Perhaps the impactor struck Mercury at a low angle rather than head-on, generating less heat while still stripping the mantle. A grazing collision between similar density bodies can preferentially remove mantle material through a process of preferential ejection without raising the average temperature of the remaining material to the degree a direct collision would. Some simulations of this scenario can produce outcomes consistent with both the large core and the volatile retention, though the parameter space of impact conditions that achieve both simultaneously is constrained. Alternative hypotheses have gained renewed attention following the messenger volatile findings. The aerodynamic drag hypothesis suggests that in the early solar system, when the Sun was still surrounded by the dense protoplanetary disk of gas and dust, the drag of gas on solid particles moving through the disk was size-dependent. Larger iron particles experienced less drag relative to their inertia than smaller silicate particles. This differential drag could have caused silicate particles to spiral inward toward the Sun and be lost, while iron particles preferentially remained in the region where Mercury formed, producing an iron-enriched starting composition. This hypothesis has the advantage of explaining the volatile retention naturally. If the composition was enriched in iron from the start rather than through a violent impact, there was no catastrophic heating to drive off the volatiles. The vaporization hypothesis proposes something different. The young Sun, during its initial contraction phase, passed through a period of higher luminosity before settling onto the main sequence. During this hot phase, temperatures in the innermost part of the disk might have been high enough to vaporize silicate minerals, but not iron-rich minerals, preferentially removing silicates from the material available to form Mercury. Again, this would produce an iron-enriched composition without the catastrophic heating of a giant impact, explaining the volatile retention. Each hypothesis has observational consequences and can in principle be tested with sufficiently precise measurements of Mercury's surface and interior. The key discriminants include the absolute abundances of specific trace elements, isotopic ratios of certain elements, the internal structure of the planet, and the detailed stratigraphy of the crust. Bepi-Colombo's measurements and potentially future missions will provide some of this information, but a complete answer will probably require either a sample return mission or in situ geochemical measurements with instruments more capable than any yet flown to Mercury. Understanding Mercury's origin is not merely an academic exercise. It connects directly to questions about planetary formation in general and the diversity of exoplanets in particular. High-density rocky exoplanets, objects that appear to have iron-enriched compositions even more extreme than Mercury's, have been detected around other stars. Whether those planets formed through giant impacts, through differential dynamics in the protoplanetary disk, or through some other mechanism is directly informed by what we understand about Mercury, the only iron-enriched rocky planet we can study in detail. Mercury's evolutionary history after its formation is also remarkable. Once formed, the planet cooled steadily over billions of years, its interior heat slowly radiating into space. As it cooled, the iron core solidified progressively from the inside out, the increasing pressure with depth eventually causing the core material to crystallize, building up a solid inner core while a liquid outer core persisted around it. This solidification released heat, the latent heat of crystallization, which helped maintain the outer core in liquid form for longer than it would otherwise have remained liquid, sustaining the dynamo that generates Mercury's magnetic field. The cooling and contraction of the planet has been expressed at the surface through the lobate scarps. Thrust faults formed as the shrinking interior pulled the crust inward and caused it to buckle. The total contraction of Mercury over its lifetime is estimated at about 2 to 4 kilometers in radius, a small fraction of its overall radius, but enough to create the network of scarps that Messenger mapped across the planet. These scarps are the geological fingerprints of a cooling, contracting world, preserved in the absence of the resurfacing processes that would erase them on a more geologically active planet. Volcanism on Mercury was significant during the planet's early history. The smooth volcanic plains that cover large portions of the surface testify to widespread lava flooding in the planet's first billion years or so, but appears to have shut down as the interior cooled and the pressure required to drive magma to the surface exceeded what the contracting mantle could provide. The last major volcanic activity appears to have occurred roughly 3 billion years ago, possibly more recently in some isolated locations, leaving a world whose surface thereafter was shaped primarily by impacts rather than internal processes. The transition from a geologically active young Mercury to the geologically quiet Mercury of today was not abrupt. It was a gradual cooling, a progressive slowing of eruptions, a decreasing frequency of tectonic events, all driven by the inexorable loss of heat to space from a planet too small to retain its warmth for long. Mercury today is a fossil of its earlier self, its surface preserving the record of those early, more active times in the craters, plains, scarps, and hollows that MESSENGER spent 4 years documenting. Let's spend some additional time with the Caloris Basin, because it represents one of the most scientifically informative features on any rocky world we've examined. The impact that formed Caloris was one of the most energetic events in Mercury's history and in the solar system's history more broadly. The impactor, estimated to have been about 100 kilometers across, based on the resulting basin size, struck Mercury at a velocity of perhaps 40 to 50 kilometers per second, releasing an amount of energy roughly equivalent to 100 trillion hydrogen bombs detonating simultaneously. The impact excavated material from Mercury's crust to a depth of perhaps 30 to 40 kilometers across a region hundreds of kilometers in diameter, through ejecta across the entire planet, and sent seismic energy through Mercury's interior that disrupted the antipodal terrain. The Caloris Basin itself, in the images from Mariner 10 and then in full detail from MESSENGER, is a dramatic sight. The basin floor has been flooded by volcanic material that erupted through fractures opened by the impact, creating relatively smooth plains within the basin interior. The basin is surrounded by a ring of mountains, the Caloris Montes, rising up to 3 kilometers above the surrounding terrain, formed from material that was uplifted and compressed at the basin rim during the impact. Beyond the mountains, a broad zone of hummocky terrain records the deposits of impact ejecta that were thrown outward from the impact site. Within the basin interior, MESSENGER's images revealed a network of ridges and troughs. Extensional and compressional features formed as the flood lavas that filled the basin cooled, contracted, and were then subjected to continuing deformation from the stresses within the planet. At the center of the basin, a cluster of ridges called the Pantheon Fossae radiates outward from a central point in a spiderweb pattern, the geological result of material being pushed upward from below and then fracturing as the basin floor adjusted to the changing stresses. The antipodal terrain, the region directly opposite Caloris on Mercury's surface, is a region of chaotically disrupted ground, sometimes called weird terrain or the hilly and lineated terrain, covering a roughly 500-kilometer diameter area. Here, the seismic waves generated by the Caloris impact traveled through Mercury's interior along multiple paths and converged simultaneously at the antipodal point, delivering a concentrated pulse of seismic energy that disrupted the surface from below. Hills, valleys, and irregular depressions created by this process have remained essentially unchanged since the impact, preserving the direct physical imprint of an impact that occurred billions of years ago. The Caloris impact is thought to have occurred during the late heavy bombardment, a period roughly 3.8 to 4 billion years ago when the Moon, Mercury, Mars, and Earth were all struck by an elevated rate of large impactors, possibly as a result of gravitational disturbances in the outer solar system that sent a wave of objects inward. The lunar record of this bombardment is written in the large impact basins visible on the near side of the Moon. Mercury's record is written in Caloris and in the hundreds of other large craters scattered across its surface. Imagine a spacecraft moving above Mercury's terminator, the line between day and night. On one side, the surface is heating under a sun far stronger than Earth's. On the other, the ground is falling into a long darkness that will last for months. There is no glowing atmosphere at the edge, no blue limb, no weather layer catching the light. The boundary is sharp because there is no air to soften it. Below, craters overlap like records of different ages pressed into the same stone. A bright young crater throws rays across darker ancient terrain. A smooth plain fills an old basin, its surface wrinkled by contraction. A scarp cuts across older craters, proving that the cliff formed after the impacts it slices through. A hollow gleams in a crater floor, brighter and fresher than the surrounding regolith. Near the pole, a crater floor remains black, not because night has fallen there temporarily, but because sunlight has never reached it for billions of years. From orbit, Mercury is not monotonous. It is a palimpsest, a surface written over many times, but never fully erased. Impacts came first in overwhelming numbers. Volcanic plains flooded some regions. The planet contracted and broke its crust. Space weathering darkened exposed material. Impacts excavated volatile-rich deposits. Hollows formed where those materials escaped. Polar cold traps collected ice. The present surface is the result of all these processes layered together. Reading that surface requires attention to sequence. If a scarp cuts a crater, the scarp is younger. If lava fills a basin, the lava is younger than the impact that made the basin. If a young crater has bright rays, those rays have not yet been darkened by space weathering. If hollows occur on a crater floor, the impact may have exposed the material that later sublimated. Planetary geology is a form of historical reasoning. The rocks do not speak in sentences, but they do preserve order. This is one of the pleasures of Mercury as a subject. It rewards viewers who like cause and consequence. Nothing has to be magical. A basin has a reason. A cliff has a reason. A magnetic field has a reason, even if we have not fully found it. Ice and shadow has a reason. The strangeness becomes more interesting when it becomes understandable. One aspect of Mercury that gets less attention than it deserves is the planet's relationship with time and with the question of how planets age. Rocky planets form hot and cool down. The rate of cooling depends on the planet's size. Larger planets have a lower surface area to volume ratio and therefore lose heat more slowly relative to their total heat content. Earth, the largest of the inner rocky planets, is still geologically active, still losing heat through volcanic eruptions and tectonic activity, still generating a strong magnetic field. Mars, smaller than Earth, cooled faster, and most of its geological activity had shut down by about 3 billion years ago, leaving behind a geologically quiet world whose active past is written in its ancient volcanoes and impact basins. Mercury, smaller still, cooled fastest and became geologically quiet earliest. But Mercury didn't become completely inert. The magnetic field persists. The lobate scarps suggest ongoing, slow contraction. The hollows are apparently still forming. These are the last remnants of a once more active world, the fading echoes of processes that operated at full intensity billions of years ago, now reduced to whispers but not yet silenced. In this sense, studying Mercury gives planetary scientists a view of what Earth and Mars will eventually become, worlds that have lost their internal heat, shut down their volcanoes and tectonics and geodynamos, and settled into a geologically quiet old age. Mars is closer to that endpoint than Earth. Mercury has been approaching it for billions of years and has not quite reached it yet. The timeline of planetary cooling and geological evolution is one of the fundamental patterns in planetary science, and Mercury sits at one extreme of the inner solar system spectrum. At the other extreme, Earth's geological processes operate vigorously and will continue for billions of years. Between them, Venus, with its apparently stagnant lid tectonics and ongoing volcanism, and Mars, with its dead core and ancient volcanic history, fill in the range. Each planet tells a different chapter of the same story: rocky worlds forming, heating up through accretion and radioactive decay, and then cooling down over geological time, their activity diminishing as their heat inventory drains away to space. In addition to all that has been discovered about Mercury, the search for what might still lie hidden beneath its surface is ongoing. Messenger's laser altimeter measured the topography of Mercury's entire surface but only at the resolution available from a spacecraft in orbit. Surface features smaller than a few hundred meters across, and features that would require surface landers to investigate directly, such as the subsurface structure beneath the polar ice deposits, the interior of the hollows, or the composition of specific geological units, remain inaccessible. Future proposals for Mercury exploration have included a surface lander, possibly multiple landers at different locations, capable of surviving on Mercury's surface long enough to conduct meaningful science. The temperature extremes present serious engineering challenges. A lander on Mercury's day side would need to survive 400 degrees Celsius, while a lander near the poles might need to function at temperatures near -200. Standard spacecraft electronics fail above about 125 degrees, and no conventional electronics can survive Mercury's full dayside temperature. Research into high-temperature electronics, primarily based on silicon carbide semiconductors, has progressed significantly and might eventually enable a Mercury surface lander that operates in daylight. But such a lander has not yet been built or flown. A sample return mission to Mercury would be even more scientifically valuable, bringing actual Mercury material back to Earth for analysis in the most sophisticated laboratories available. But the energy required to both reach Mercury's orbit and then return to Earth is enormous, making sample return significantly more challenging than for destinations like the Moon, Mars, or even some asteroids. Nevertheless, preliminary studies of a Mercury sample return mission have been conducted, and it remains a long-term aspiration for the planetary science community. What a Mercury sample would reveal: the isotopic composition of its materials, the trace element chemistry in microscopic detail, the age of specific geological features determined by radiometric dating, the nature of the volatile elements, and what they tell us about formation conditions, would transform our understanding of inner solar system formation in ways that orbital measurements alone cannot achieve. The Apollo lunar samples transformed our understanding of the Moon's origin and history. Mercury samples would likely have a comparable scientific impact. Until that day, Bepi-Colombo's measurements from orbit, the continued analysis of MESSENGER's extensive dataset, and Earth-based observations will continue to push the boundaries of Mercury knowledge. The planet has gone from a moving point of light, unknown for most of human history, to a world with a surprisingly complex geological story, a puzzling magnetic field, and a set of open scientific questions that will occupy planetary scientists for decades. That is, in itself, a remarkable transformation. And it was accomplished mainly by Mariner 10 and Messenger, two spacecraft missions separated by nearly 4 decades, with Bepi-Colombo now preparing to add the next layer of detail. Mercury has given up far more than most people expected from such a small, apparently simple world. The most unglamorous planet in the solar system keeps proving that unglamorous and uninteresting are not the same thing. Beyond the major open questions about formation and magnetic field, Mercury presents a number of specific puzzles that current data cannot resolve. The volatiles problem is central. Messenger found volatile elements at Mercury's surface in quantities that are difficult to reconcile with any formation scenario that involves high-temperature processing. The abundance of sulfur, which has a relatively low volatility, is particularly challenging because sulfur should have been depleted by any significant heating event, whether from a giant impact or from early proximity to the luminous young sunday, explaining how Mercury managed to retain sulfur in its current quantities, despite the apparently severe conditions of its early history, is a problem that current models have not fully solved. The origin of the hollows is not fully established. The sublimation hypothesis, that volatile-rich patches of surface material are being eroded by solar heating, is plausible and has good observational support, but the identity of the specific volatile materials being lost remains uncertain. Are they sulfur compounds, volatile metals, or something else? The answer matters because it would both identify the chemical nature of Mercury's surface material and constrain the rate at which the hollows are forming and growing. The interior structure remains imperfectly constrained. Messenger's gravity measurements established that Mercury has a solid inner core, a liquid outer core, a possible solid silicate layer above the outer core, and a silicate mantle and crust above that. But the thicknesses and compositions of these layers are still uncertain at a level that matters for understanding the dynamo and the thermal history. Bepi-Colombo's gravity measurements, expected to be more precise than Messenger's, will help narrow down these uncertainties. The history of Mercury's volcanic activity is not fully reconstructed. Messenger established that significant volcanism occurred in Mercury's early history and mapped the extent of the volcanic plains. But the detailed timeline, when volcanism was most intense, when it declined, whether it has ceased entirely or might still be producing minor eruptions, is not settled. Some observations hint that Mercury's volcanism may have persisted later than previously thought, potentially into more recent geological time. And there are questions about the chemistry and dynamics of the exosphere that require the more sensitive instruments aboard Bepi-Colombo to address properly. How does the exosphere respond to solar storm events? When the solar wind intensity temporarily spikes? What is the detailed composition of the calcium component, which shows unusual spatial distribution in Messenger observations? How do the exospheric abundances vary with Mercury's position in its elliptical orbit as the distance to the Sun and the solar wind intensity change substantially? These open questions are the productive kind. They are not signs of ignorance, but the natural result of having studied something carefully enough to know what you don't yet understand. Mercury, which was a near blank for most of human history, is now known well enough that the edges of current knowledge are clearly defined. Bepi-Colombo will push those edges further, and future missions, surface landers capable of surviving the extreme temperature cycle, eventually perhaps sample return, will push further still. Mercury also marks an inner boundary in the architecture of the solar system. Beyond it, there are no planets closer to the Sun. The region inside Mercury's orbit is not empty, but it contains no stable major world. Dust, small asteroids, and fragments may pass through, and there are populations of small bodies influenced by the Sun's gravity, but no planet like Vulcan was ever found. Mercury is the last survivor at the inner edge. That inner edge matters because planet formation close to a star is difficult. Temperatures are high. Orbital speeds are high. Collisions are energetic. The young star emits strong radiation and charged particles. Materials that would remain solid farther out may vaporize or migrate. The composition of planets formed there can differ sharply from the composition of planets formed only slightly farther away. Mercury's iron-rich nature may therefore be telling us not only about one planet, but about the harsh environment of the innermost protoplanetary disk. Around other stars, we now see planets much closer to their stars than Mercury is to the Sun. Some orbit in days, not months. Some are so hot that their surfaces may be molten lava. Some may be stripped cores of former larger planets. Some have densities suggesting extreme iron enrichment. Mercury is not as extreme as those worlds, but it is the nearest local example of the physics that begins to dominate close to a star. This makes Mercury a bridge between the familiar rocky planets and the stranger exoplanet population. Earth, Mars, Venus, and Mercury are not just four local objects. They are four examples of how rocky planets can turn out: habitable and wet, cold and thin-aired, greenhouse-dominated and hostile, or airless and iron-rich near a star. Exoplanets fill in many more combinations, but Mercury anchors one end of the range. If we want to understand whether a dense close-in exoplanet is a stripped mantle, a naturally iron-rich planet, an evaporated remnant, or a collision product, Mercury is where we test the ideas first. It is the only such world whose surface we can map in detail, whose magnetic field we can measure directly, whose exosphere we can watch change with solar wind, and whose formation history can be constrained by actual chemistry. That is a large role for the smallest planet. There is one more perspective on Mercury worth considering, and it connects Mercury to the broader universe in a way that makes it more than just a local footnote. Hot super-Earths, rocky exoplanets with masses between 1 and 10 times Earth's mass, orbiting very close to their host stars, are common. The Kepler Space Telescope and its successors have found hundreds of them. Many of these planets orbit so close to their stars that they are tidally locked, or nearly so. They keep one face permanently toward the star, just as the Moon keeps one face toward Earth. Their surface conditions are extreme. Intense solar radiation on the permanent day side, extreme cold on the permanent night side, potentially powerful atmospheric circulation driven by the temperature contrast. Mercury sits in an interesting position relative to these exoplanets. It is not tidally locked, but it is in a spin-orbit resonance that is a step toward tidal locking. It is iron-enriched in a way that may be common for the innermost rocky planets around stars. It has essentially no atmosphere, another state that rocky planets close to their host stars often evolve toward as atmospheric gases are stripped away by stellar wind. In a very real sense, Mercury represents what many of the innermost rocky exoplanets may look like. Iron-heavy, airless, tidally influenced, with extreme temperature swings between the illuminated and dark regions, and a geologically complex interior that is still evolving. Understanding Mercury in detail, therefore, has direct implications for interpreting the exoplanet population. When astronomers measure the density of a distant hot super-Earth and find it is iron-enriched, Mercury provides the best local reference for what such a planet might look like up close. When models predict that close-in rocky planets should have thin exospheres produced by the same processes that generate Mercury's, photon-stimulated desorption, solar wind sputtering, meteorite vaporization, Mercury's exosphere is the observational anchor for those models. When theorists ask whether a magnetic field can survive on a small, close-in rocky planet, Mercury's improbably persistent dynamo provides both a data point and a puzzle. Mercury is, in this sense, the solar system's best natural laboratory for understanding the physics of rocky planets at close stellar distances, which is to say, the physics of the most common type of rocky planet we've discovered around other stars. The next set of Mercury questions is specific enough that it shows how far the field has advanced. The first question is the core. How large is the solid inner core? How thick is the liquid outer core? Is there a stable layer near the top of the core that suppresses the magnetic field? What light elements are mixed with the iron? These are not details for specialists only. They determine how a small planet can stay magnetically alive. If Mercury's core contains sulfur, silicon, or other light elements in the right proportions, its melting behavior changes. If the core is layered, convection changes. If convection changes, the dynamo changes. A small difference in chemistry can decide whether a planet has a magnetic field. The second question is the mantle and crust. How thick is Mercury's silicate shell? Did the crust form from a magma ocean? Did graphite float to the surface and create an early dark crust? How much of that crust survived later bombardment and volcanic flooding? The answers would tell us whether Mercury's surface is mostly a later volcanic skin or partly a preserved remnant of the planet's earliest differentiated layers. The third question is the volatiles. Which minerals host Mercury's sulfur, sodium, potassium, and chlorine? Are the hollows caused by one dominant volatile phase or by several? Are hollows forming today, or are they geologically young but not currently active? How fast do they expand? What does their distribution say about buried composition? These are questions an orbiter can approach with imaging and spectroscopy, but a lander or sample would answer much more directly. The fourth question is the polar ice. How pure is it? How thick are the deposits? How old are they? Were they delivered gradually by many comets and asteroids, or could one or several large impacts have deposited much of the inventory? Does the dark material above some deposits contain complex organics? The polar traps are not simply frozen curiosities. They are archives of volatile delivery to the inner solar system. They may preserve samples of material delivered from asteroids or comets long after the rest of Mercury's surface was sterilized by heat and sunlight. The fifth question is the exosphere. How does it respond to solar storms? How quickly do sodium, calcium, potassium, oxygen, and other species vary through Mercury's orbit? How does the magnetosphere control where atoms are removed from the surface and where they escape? This is a planet where the boundary between surface and space is not separated by a thick atmosphere. The surface is directly plugged into the solar environment. The sixth question is formation. Was Mercury made iron-rich by a giant impact, by sorting of material in the early disk, by evaporation near the young sun, or by some combination of processes? Each explanation changes how we interpret close-in rocky planets around other stars. If giant impacts can create Mercury-like worlds, then dense exoplanets may be collision remnants. If disk chemistry can create them naturally, then high-density planets may form close to stars without needing catastrophic stripping. Mercury is the test case. These questions give the planet momentum as a subject. It is not a solved world waiting for a summary. It is a world with a research program. For a viewer, Mercury's appeal comes from this reversal of expectation. It begins as the planet that seems least likely to surprise. Then each major fact undermines that assumption. The closest planet is not the hottest. Venus is hotter. The small planet has a huge core. The airless planet has water ice. The dead-looking planet has a magnetic field. The simple orbit became evidence for relativity. The cratered surface contains features seen nowhere else. The planet that looked like a moon turned out to be chemically and geophysically distinct from the moon in crucial ways. This structure is strong because it gives the audience repeated moments of correction. The viewer starts with a simple mental picture and keeps having to revise it. That is one of the best ways to hold attention in a long science script, not by making everything loud, but by making each section change what the viewer thinks the planet is. Mercury is not dramatic in the obvious cinematic way. It has no storms to show, no clouds to move, no ocean to glint, no rings to frame the shot. The drama is intellectual. It is the feeling of realizing that a small gray body can contain a chain of problems that reach from ancient astronomy to Einstein, from impact physics to exoplanets, from the deep core to frozen water in darkness. A strong Mercury episode should therefore not apologize for the planet's quietness. It should use it. It should say, "Look closer." The closer you look, the stranger it gets. Mercury also changes how we think about the word dead in planetary science. It is tempting to divide worlds into active and dead, living and frozen, dynamic and static. Earth is active, Io is active, Enceladus is active. Venus may be volcanically active. Mars is mostly quiet. Mercury would seem to belong with the dead worlds. But the real picture is more nuanced. A planet can be geologically quiet and still evolving. It can lack volcanoes and still contract. It can lack atmosphere and still have an exosphere. It can lack weather and still have a surface reshaped by solar wind. It can be small and old and still maintain a magnetic field. Mercury is not alive in any biological sense, and it is not geologically active in the way Earth is. But it is not finished. Its core is still important. Its weak magnetosphere still interacts with the sun. Its exosphere is still regenerated every moment. Its hollows may still be changing. Its polar ice remains stable only because geometry protects it from sunlight. Its cliffs record ancient contraction and perhaps some younger deformation as cooling continues. This kind of world is scientifically valuable because most rocky planets in the galaxy may be closer to Mercury than to Earth. Earth is exceptional, wet, tectonically active, biologically transformed, protected by a thick atmosphere and strong magnetic field. Mercury is closer to the stripped-down baseline of rocky planetary physics. It shows what happens when a rocky world is exposed, compact, iron-rich, airless, and close to its star. That does not make it less interesting. It makes it fundamental. If a viewer sees Mercury as a gray cratered ball, the story ends quickly. If they see Mercury as a test of relativity, a fossil of planetary formation, a magnetic puzzle, a thermal extreme, an archive of impacts, a volatile mystery, and a local analog for close-in rocky exoplanets, the small planet becomes enormous in meaning. That is the point of Mercury. The drama is not in clouds or oceans or rings. The drama is in the fact that a world can look almost empty and still contain some of the hardest questions in planetary science. Mercury is not a planet that asks for your attention. It doesn't do anything dramatic enough to demand it. It's too small to dominate the night sky, too close to the sun to be easily observed, too airless and geologically quiet on its surface, at least on human timescales, to produce the kind of spectacular events that make other planets famous. If you look for it at all, you'll find it low on the horizon for a brief period in the evening or morning twilight, bright enough to notice if you know where to look, small enough that even a backyard telescope shows little more than a tiny disk. But look at it again, knowing what you know now. That point of light is a planet with an enormous iron core constituting 3/4 of its mass, maintaining a magnetic field that no straightforward physics explains. A planet that shrank over its history, carving cliffs hundreds of kilometers long across its surface. A planet whose orbit carries a measurable signature of the curvature of spacetime. A planet that spins in a precise 2 to 3 resonance with its year, producing a solar day nearly twice as long as its year, and a sun that reverses its direction in the sky. A planet with water ice in permanent shadow while 400 degrees of heat bakes the sunlit terrain nearby. A planet whose surface is growing hollows that shouldn't exist at rates fast enough to be geologically recent. All of that in a world smaller than some moons. All of that in the most easily overlooked planet in the solar system. The universe tends to reward careful attention. Mercury is one of the more striking examples of what rewards looking closely at things that seem, at first, too small and too ordinary to bother with. The strangeness was always there. It just takes patience and the right instruments to see it. There is one final way to understand Mercury, as a planet of edges. It sits at the edge of visibility, close enough to the sun that human eyes can find it only in the narrow margins of dawn and dusk. It sits at the edge of thermal survival, with one landscape cycling between intense heat and deep cold. It sits at the edge of atmospheric existence, not quite airless in the strictest sense, but possessing only a thin exosphere that is constantly created and lost. It sits at the edge of magnetic survival, maintaining a weak field when a small planet might have been expected to fall silent long ago. It sits at the edge of planetary formation models, challenging every simple explanation for how a rocky world should be assembled near a star. Those edges make Mercury valuable. A middle case can be comfortable but less revealing. Extreme cases expose the limits of theory. Mercury tells us where models strain. How much volatile material can survive close to a star, how small a planet can be and still keep a dynamo, how a planet's orbit can preserve relativistic physics, how long polar ice can remain stable under permanent shadow, how impacts and contraction shape a world without weather. Even the fact that Mercury has no moon is part of the story. There is no companion to raise strong tides, no moon to stabilize a large axial tilt, no secondary world to preserve a shared history. Mercury moves alone. Its environment is dominated not by a moon, but by the sun. The star is the central actor in Mercury's sky, in its orbit, in its exosphere, in its surface chemistry, and in the difficulty of reaching it with spacecraft. That closeness to the sun can make Mercury feel hostile, but it also makes it honest. There is no atmosphere hiding the surface, no ocean burying the crust, no vegetation altering chemistry, no plate tectonics rearranging the evidence. The record is damaged by impacts and modified by space weathering, but it is still direct. Mercury is exposed. That exposure is harsh, but scientifically it is revealing. So the smallest planet becomes a kind of archive, not a gentle archive, not a complete archive, but an archive of what happens to rocky matter under the full pressure of the inner solar system. Mercury is still there, close to the sun, moving through its quick elliptical orbit, carrying evidence of impacts, contraction, magnetism, ice, heat, and relativistic gravity on a surface smaller than some moons. It has been doing this for 4.5 billion years. The smallest planet is not simple. It is a compressed record of the inner solar system, written in iron, shadow, sunlight, and stone. Good night.